Right. I think yesterday we stopped when we were discussing the domain. Is it domain of the function? Right. Now, I would try to highlight now two types of functions and try to highlight what you must focus on when you are analyzing domain. For example, let's talk about the rational function. Rational functions. Rational functions, as you know, if I've got r of x as a rational function, that function must be something like p of x over q, or sorry, I'll say g of x there. But let me just adjust that. I want to say q of x. Now, obviously q of x is the denominator, is it? So wherever that function is defined, q of x must be, can you tell me? Might not be equal to 0. Okay, that's important, isn't it? Right. Now, so in talking in terms of the domain, when you want to check the domain of the function, which is a rational function like this one, I think the most important thing is to get hold of the denominator. Now, the most critical thing is the denominator. In this case, the denominator is q, isn't it? So, what must you do with the denominator? You must actually create an equation using that denominator, q of x an equation and equate it to 0. To 0. What am I trying to say there? When you identify the zeros of this q, then you will identify those points which are a problem for the rational function. However, the zeros for q, we call them poles for rx. You understand what I'm saying? You find the zeros here, zeros of q of x. Those zeros of q of x, we call them poles of the rational function, in this case r of x. Am I making sense there? Sorry? What is not making sense? A zero of a function, I mean, if you equate q to 0, you solve the equation. The answers you get, you can call them zeros of q. Is that right? But that zeros of q, when we talk in terms of r of x, we call them poles of r of x. Am I making myself clear now? Okay, let's get an example. Let's say we've got a function here, a rational function, which is equals to 2x over x minus 1 brackets x plus 2. I'm giving you already factorized so that you can easily see what's happening. Now, if I'm going to look at the domain of the function, this type of function, since it's a rational function, remember I've got to cut against things like this. 0 over 0, number a over 0, because those are undefined entities, isn't it? So now, if to check something like this, the only thing I can do is to take x minus 1 brackets x plus 2 and equate it to 0. All together. That's mathematics, no? Okay? Are you coming to mathematics, okay? Okay. So, immediately, this is easy. I mean, this definitely, if you wrote metric last year, there was something like this in the paper, isn't it? So, you know that x here is going to be equal to 1, or x is equal to minus 2. So those are the zeros of what? Of q, isn't it? So because this is our q, our denominator for the rational expression. So those are the zeros of that. Now if I'm going to now discuss the domain of f, I'll write there df to say the domain of f. What's that going to be? It's going to be a set of rational numbers, because remember now we're dealing with a real line, rational numbers, those rational numbers such that stroke there says is a word which says such that when you read that stroke, read it as such that x is not equals to 1. Why? Because if x is equal to 1, we're going to have something like this, isn't it? And we can say, oh, x not equal to 1 and x is not equals to minus 2. So that gives us the value, the part where the function, the rational function is defined. Altogether, that is very important. So, emphasis for rational functions, always you must be careful with the denominator. You cannot decide on the domain without knowing what are the zeros of the denominator or what are the poles of the function itself. Isn't it? So guys, is it clear the term pole and the zero? What I mean by pole and what I mean by zero. There, pole and there, zero. You must see that zeros there in terms of that situation, I'm talking about zeros of denominator. But when I'm talking about poles, I'm talking about the poles of the whole function. Altogether. So those are the terms and the terminology you must learn and from now on forever if you don't know them. Is that all right? Okay. So, can I move on? Can we move on? Okay. Now let's come to, I want to discuss now the domain of an expression like this one. Domain which involves radicals. Remember, if we can have something, an expression like this, and say 3 minus x. Let's say we say that is a function. In this case, to make a square root a function, we can just decide to take the principal square root. In this case, we are only considering the positive square root. That's right. Okay. So in this case now, if somebody wants to say now, what is the domain of this function? What is the theory you must have? First, you must have the theory that this is not acceptable under the radical sign whenever x is greater than 0. Because if x is greater than 0 minus x is negative, isn't it? So this is not acceptable. So what is acceptable? What is acceptable is that whenever I've got a square root of x here, just as a placeholder for any number, that x must be greater or equals to 0. Is it? Right. So now when I give an expression like this, what is my x? Remember I said the x is a placeholder of anything other than there, isn't it? So my x in this moment here, my argument of that radical sign is what? Is 3 minus x. So then you must actually follow this and say, to find the argument of this will only work when 3 minus x is greater or equals to 0. What is that? That's an inequality, isn't it? An equality you know, then you must solve it. And it's solved like an equation. Whatever you do on one side of this equal sign, you do on the other. Listen, in my language, nothing moves. Nothing moves across the state, not really in my language, in the math language, nothing moves across an equal sign and change sign. There's nothing like that. Now, what happens? In this case here, we've got it 3 minus x greater or equal to 0. We want to solve this and want to have a condition which is on x, isn't it? So first of all, we need to leave x alone on one side of the equation, isn't it? One way I can do it is to add on both sides minus 3. If I add on both sides minus 3, I'm going to have minus 3 plus 3, this 3. Altogether, minus x greater or equals to 0 plus minus 3. Is that right? I'm adding on both sides minus 3. Are you confused? What is confusing you? Or you are not? Okay. What's going to happen here? We know numbers have got a property that if I've got A, I add A to minus A, I will always get a 0. So that guarantees us that here we're going to be only left with x minus x. We're going to be left with minus x. Then that greater than 0 minus 3 plus minus 3 is actually minus 3, isn't it? We can use also the combination of signs there. Then we've got minus 3 there. So, do you want minus x or want a condition on x? We want a condition on x, isn't it? Then there's another property you must remember there. What you need to do, if you want x there, then which means this expression, we must multiply it by minus 1. Because you remember, minus and minus, they produce us a positive, isn't it? Okay. So, but there's something which happens if you multiply inequality by minus 1. What happens? It reverses the orientation of the sign, isn't it? Which means now here, what we're going to have? We're going to have x less than or equals to 3. Are we together? Yeah. I could have put here all this thing here. I could have put equivalent signs here. That the statement above is the same as this one. The statement above is the same as this one. That sign, I'm saying this is equivalent. Are we together? But let me just put a partition there, not to confuse you. Let me take another color there. I want to put this thing here. Oh, what did I do? I want to put this thing here in a box so that I can avoid that equal sign there. Right. So the most important things we have used here, you have known that minus 1 times minus 1 gives us plus 1. Those are properties of numbers, isn't it? The combination of signs. So now, do you see what happens now? So what does that say here? Is this thing says now, this is going to be defined only when x is less than 3. Is it? So what should we do now? Now we'll say domain of f is equals to real numbers x such that x is less or equals to 3. All together. Okay. So guys, that is, you must be very careful when you come to these things of analyzing a domain for everything. Then the other thing we're going to talk about, we talked about briefly, is the range. All together. Now let's briefly look at what do you mean by the range of a function. The range. Now, in simple words, when I'm talking about the function f of x, let's say y is equal to f of x. So the range becomes the collection of all the outputs of that function, of all the values that function takes. Like for example, let's take an example of a function like y is equals to x squared. Roughly everybody knows this function. This is the parabola, the simplest parabola without any kind of transformation. We'll talk about those things, how to transform some of these things, and they vary some parameters to get different parabolas. Then, roughly sketched, that function is like that. Now, if you would analyze the domain of this function, let's talk about the domain of this function. Is there any value you can think of which will make this thing undefined or not make sense? Yes or no? Something which will produce a value, a number which is going to produce something like 0 over 0, something like a number a over 0. or something like infinity 150. Is there a number you can think of on the real number line? Real number line, I'm talking about this line here, the real axis here. Is there a number we can cause this to multiply? What does that mean? It means the domain is precisely all the real numbers, isn't it? Okay. Now when you come to the range, maybe let me just use that RF like that for the range to keep in like similar to what I've used, notation I've used there for the domain. Range of f. Now, what is the range of f? I said the range of f must be all the set of values the function picks as you input x. Isn't it? We can start at 0. If we start at 0, there, what's the value of the function there? What is y? Remember, I said if you are looking at a graph of a function like this, you must always keep this in mind. If you're looking at a graph of a function like this and you've got a point there, always you must understand that that point coordinate is x, comma, f of x. Do you understand that? Now, where is x from? X is from the real line there. There is x. And the f of x is the value of y there. Maybe let me clean that a bit so that we don't have some confusion there. So somewhere there, that's where we have the value y, and somewhere there, that's where the input x is coming from. Are we together, guys? So that is where x is. So now when I'm at this point here, this where x is 0, our x is actually 0 and our y is 0. So which means this 0 is actually in the range. To say 0 is in the range, you can say 0 is in the range of f, isn't it? In other words, it's a member of this set. Now, if you pick another x here, let me use a green color there. If you pick another x there, the corresponding y is going to be there. If you pick another x there, the corresponding y is going to be there. If you pick x in the negative there, the corresponding y is going to be there. Isn't it? So now, is this going to stop? As you go up, you're going somewhere there, you're going to cut the parabola, and the y's are going to be there. Isn't it? What does that tell us? It tells us that the range of this function starts from 0 going to infinity. Is that right? So then you can now write here the range is x. Oh, sorry, the range I'll use y. Ne? Please, I'll use y there. Let me just finish writing there. Y such that y is greater or equals to 0. Then let's correct this. Let's correct this here. There's somebody talking here. Ne? Is it in this class? Outside. Can you close that door, please? Sorry, guys. Please don't disturb us, man. If you're coming in, come in, but don't do that. So that is the range, is it? Obviously, this is an example, and I used a simple example so that you can get the idea of what's happening. So different expressions will present you different challenges. So what you need to do there, you need to actually break down the function, unpack it, and see exactly where is the range. That is the task you're supposed to do, isn't it? Yeah, like as usual, you know, teachers do simple examples in class and leave the difficult ones for students to learn and grow. All together. That's a nice setup, no? You don't like it, but everyone goes through that. No? But obviously, if I say do the difficult example, then you might find that you don't understand what's the gist of the thing. But if you look at this difficult example with an understanding, then you might find a way of going around it, or even ask that I'm up to here, I can't go further. Then that's where you learn. Are we together, guys? Okay. Now, from here now, I'm going to move to another concept of a function which you need to understand. But maybe before I do that, let's talk about functions which have got a restricted domain. We've already seen that. When we say function has got a restricted domain, like the domain of x squared is not restricted. It's just that. Now, but if we get an expression like f of x equals to 1 over x minus 1, then that domain is restricted in such a way that 1 is excluded, isn't it? Also, if you've got g of x equals to square root of, let's say, x plus 4. Also, the domain of this function is going to be restricted, isn't it? So, find the domain of this function and find the domain of these two functions and see how you have to take the real number line and restrict them to a certain region of the line, or so on. Altogether, that's the concept of a restricted domain. Then the next thing is a function which is piecewise defined. Like the function I've got here, like for example, let me write another function here. Let's say h of x, which is equals to x squared plus 3x plus 1. That function has got just one expression which is defined for the whole of its domain. It's not piecewise defined. Altogether. So, but sometimes, let me write this word here. So it's piece. I don't know whether my spelling is correct. Piece is P-E, no? For a piece, it's P-E first, isn't it? Yeah. Sometimes these things are problematic. Remember, English is a very problematic language. Sometimes it sounds like something and you write something. Right. Piecewise defined functions. Altogether. That's what we're discussing now. That's the term. You have to understand that term, piecewise defined function. Now I'll just clean up that and say again the piecewise defined functions. Now, what are we talking about there? Now, there are sometimes we need to define a function and restrict some part of the function to a certain domain, the other part to another domain. Like, for example, let's take y, or let's say y is equal to f of x, and the f of x is defined this way. We use this kind of bracket there. Then we say this function is minus x for all x less than 1. And then you can say this function is 1 for x between 1 and 2. And then I'll say the x is equal to f of x equal to x when x is between let me say infinity there, then here less or equals greater or equals to 2. If you look at my use of inequality signs there, I've been very, very careful with that. Just check what's happening there. Maybe you can tell me why if you think what is the reason I did that way. Look at this here. It says strict inequality. there, it's a strict inequality. But when I use 2 here, I use less or equal. Why do you think I did that? Think about what we say the function is. We say the function is a kind of an expression or a machine or an assignment such that given an input should give us a single output altogether. So now, if I put equals there and the equals there, this function is going to have 2 values at the same point. Is that right? And even there, it's going to be defined differently to a single point. That's not right. We must be careful with that. So if we have a function like this, we say its function is piecewise defined. If we want to represent the function graphically, you must take into account those different partitions of the domain. Now we've got a point here which is 1, which is the point which is useful. We've got a point there which is 2, which is also useful for definition. So a line x minus 1 is a line. Y is equal to minus x is a line which will come this way. The bisector of what? Of the third, second, and the fourth quadrant, isn't it? Then you will see that that function at 1 exactly, x does not touch a 1, so which means the function is not defined there at 1. So there we put an open circle there to say that domain, that part of domain does not touch 1, is indicated by that circle there. Am I making sense? That's an indication that from the left, I don't go as far as 1. I go strictly below 1, but as close as possible, altogether. Then when I start to come here, the function is 1 between that and that. So at 1, the function is assigned the value 1 because it says x equal to 1. So then I've got something there, 1. Now as I can say, this here is a 1. And maybe here, this is actually minus 1 according to the definition of function. So you see now, if I put equal sign at 1 there, then this will be a dot and that's a dot, which would mean at 1, the function has got 2 values. Do you see that? But the function is not supposed to have 2 values at a given input. So then from there, it is constant, it's 1 until as close as possible to 2, but does not get to 2. Altogether. Then from there onwards, it's x equals to y is equal to x, which means if this is 2 and this is 2, exactly at the point 2, 2 there, the function will start and go up as usual. Sorry for that overwriting there, but I hope it's clear to everybody. It's not confusing, isn't it? I mean, I'm saying sorry for writing over there because it looks a bit clumsy. It was not supposed to be like that, but this is something I'm just writing as we're discussing. Is it clear? Okay, so that's a piecewise defined function. So the graph also is given in pieces. Is that clear, guys? Exactly what I've explained here, the dots, the open circles, and everything, are things you're going to be asked to show your understanding of and actually prove to anybody out there that we discuss this thing just and you know what it means. Okay, so I think I've discussed graphical representation of function. This is one of them. And the other thing is, functions sometimes can be given by way of a statement. Look at the study guide. You see somewhere in the pages dealing with functions, they give examples of how you can define a function, not by really mathematical expression, but although that statement also can be translated into some kind of mathematical expression. Right. Okay. So I'm feeling let's just stop there for a while and just reflect on what you've said. The recording is